Well, we've already stated theorem 2.4, so I've chosen one of them for which we're going to prove. Theorem 2.41. This is the reminder of what it said. The limit of f of x is equal to capital L, the real number, as x goes to x naught, and the limit as x goes to x naught of g of x is the real number capital M. If those two things are true, that implies that the limit as x goes to x naught of f plus g of x is equal to L plus M. Now, one thing I didn't write in this little summary is that we're assuming x naught is an accumulation point of the domain of these two functions, capital D. Well, I'm actually going to do two different kinds of proofs. The first one, proof one, is going to be the delta epsilon proof. So we're going to use the definition of what it means to have a limit, a function having a limit. Well, anytime we do that, here's what we're proving. If I want to prove that the limit of this function as x goes to x naught is L plus M, I need to start off by taking an arbitrary epsilon greater than 0. And what do I need to find? I have to find a delta greater than 0 such that every time x is in the domain and very close to x naught, within a distance of delta of x naught, that implies that this new function f plus g of x minus its limit L plus M is less than delta. So that came right from the definition of what it means to be the limit of a function at a given point. Okay, well, let's write down now the things we know. Since this is true, the limit as x goes to x naught of f of x is equal to L. Since that's true, there exists a delta. I'm going to call this one delta 1, greater than 0, such that the following holds true. It's going to look very much like that statement over there. If x is in the domain, capital D, and x is very close to x naught, and specifically within delta 1 of x naught, that implies that f of x minus L is less than, I'm going to use epsilon over 2. We've seen this kind of a proof before. I'm able to say that because this is true. If this is true, then this is just the definition of what it means for that limit to exist. Now I'm going to write another sentence that looks almost exactly the same as that, replacing f with g and one other minor change. Since the limit as x goes to x naught of g of x is equal to capital M, there exists a delta 2, it may not be the same delta as that, greater than 0, such that x in the domain and x very close to x naught, and in this case, between 0 and delta 2 of x naught, since that's true, there exists this, and that means that whenever x is in the domain and close to delta 2, g of x minus M is less than epsilon over 2. So both of those sentences are due just to the fact this limit exists and this limit exists. So essentially, to conclude this, I just need one more sentence with a little bit of algebra. Therefore, for delta equaling the smaller of the two, the minimum of delta 1 and delta 2, that will mean that if x is within delta of x naught, then both of these is true. That means it's within delta 1 and it's within delta 2 of x naught. Because delta is the smaller of the two, we have the following. X in the domain and 0 less than or equal to x minus x naught in absolute values, less than delta, which means this is true and this is true. That implies that what we're looking for is, I'm going to rewrite f plus g of x is equivalent to this. I just wrote it separately here. And minus L plus m is the same as minus L minus m. So this is exactly equal to what's in absolute values here. Exactly what's equal to what's in absolute values there. And I'm going to show that that's less than epsilon. Okay, that there is less than or equal to f of x minus L plus g of x minus m by the triangle inequality. Maybe I skipped a step in reordering this. I could have reordered this to be f of x minus L plus g of x minus m, and then it easily follows that we're using the triangle inequality in that second step. Well, because all of that's true, I know f of x minus L is less than 1/2. Sorry, epsilon over 2, not 1 over 2. And g of x minus m is less than epsilon over 2, and that's equal to epsilon. And that's all we had to show to complete the proof. We found the delta such that if x is in the domain, capital D, and x is within delta of x naught, we see that this is true right here.